We have a couple basic log properties that we can use as shortcuts when we do come across some of these logs that we have to evaluate from time to time. These properties do provide us with shortcuts. If you ever forget the property, you can still come out with the right answer. But it's always good to just kind of have these in the back of your mind and know that they're there, because it can save you some time as you're working through some of these problems. So the first one says that if you have log base b of b, that's actually just equal to 1, because 1 is the exponent to which b must be raised to obtain b. So we'll prove that example and show you what that means. But it's basically saying if you have log base b of b, so if your log base and what you're taking the log of is the same, if we recognize that, we know the answer is just going to be 1. So down here on example A, log base 7 of 7 is just going to be equal to 1. The second property is log base b of 1 equals 0. And what this is saying is if you take the log of 1, no matter what that base is, if you take log base 2 of 1, log base 3 of 1, log base 4, 5, 6, 7, e, whatever the log is, if you're taking it of 1, it's always going to be equal to 0. So the example B down here, it's log base 5 of 1, but you're taking the log of 1, so the answer is going to be 0. So let's look at the proofs of these, just to show you why these are the way they are. If I take log base 7 of 7 and I ask you to evaluate that, so I want to know what is that equal to. If I take it out of log form and put it into exponential form, moving the base over, this becomes 7 to the y power. All you have left over here is 7, and you can see that y is equal to 1. If these are going to be equivalent, y is equal to 1. So either way, if you work it out the long way, you're still going to get 1. So these just provide us with some shortcuts that will save us a little bit of time. Now over here, if I wanted to evaluate log base 5 of 1, set it equal to y. Again, if I take the base and move it over to the other side, this is 5 to the y power equals 1. And rules of exponents say anything to the 0 power is always equal to 1. So that's how we know that y is equal to 0 on example B. Okay, so those are the two basic ones. A couple more. These are inverse properties of logs. The first one here is very similar to the first basic log property from above that said log base b of b is equal to 1. Well, this says if you have log base b of b, but your b also has an exponent attached to it, then your answer is just that exponent. So for instance, if you look at example A down here, if we had log base 4 of 4, we would know that's a 1. But because that 4 has an exponent up there, my answer is just that exponent. And basically it kind of works like this. Because your log base 4 of 4 is just equal to 1, usually we say, like anything divided by itself is 1, we cancel it out. It kind of works. You can kind of think of it like that. Okay, but let me show you the proof of this one. If we had log base 4 of 4, and that 4 is to the 5th power, and I wanted to know what this is equal to, if I convert this into exponential notation, all you have left over here on the left side is 4 to the 5th power. So you can see that for these to be equal, y has to be equal to 5. So again, it's one of those things you can always go through the proofs and still come out with the same answer. Now this one is a little bit more complicated. It says if you have a base of b and it's raised to log base b of an x, your answer is actually just that x. So your answer on this one is just 9. So again, that one is not one that you will see that often. You'll see the first 3 more than you would see this one. But this one, just by looking at it, we know the answer is 9 because of the property. But let me show you how to prove this one. This one is a little bit more complicated. If I have 6, that's my base, and it's raised to an exponent, and it just so happens my exponent is a log, and I wanted to know what this is equal to. Now, this one is actually in exponential form because you have a base and an exponent. Now, it does have a log, but log form has to be y equals log base b of x, and this does not fit that form. There's a log, but it's in the exponent. So since we have an exponent, this is an exponential form. So if you remember from a previous video where we learned how to go from exponential form to log form, what we have to do is take the base moves over to the other side and becomes the base of the log. So over here I'm going to have log base 6, and all you have left over here is a y. If the base is gone, all you have left over here is log base 6 of 9, and you should be able to see now at this point, doing our conversions, that y, if those are going to be equal, they both have log base 6, they have the same bases, just like we have with exponential form, just like we had over here. As long as the bases are the same, then everything else has to be the same. So log base 6, so you can see there why we get an answer of 9. Okay. Some of the other properties of logs that we have deal with common logs. Now, this is something that you want to keep in the back of your mind. You need to know the name of the log and then what it is. And the common log, and we've mentioned this briefly in a previous video dealing with these logs, that the log button that you have in your calculator is programmed to a base of 10. And this log has a special name, and it's called the common log. And it's one of those that it's understood that if you have log base 10, if you can actually see the base of 10, since that is our common log, we can also write that without the base, and we can write that as just log x. So you have to have a base. A log has to have a base. So there has to be something there. So it's understood that if you don't see anything there, if you see just log of x, it is understood that there is a 10 there, because that is just our common log. Now, that is similar to, for instance, taking an x squared. We know that there is actually a 1 in front, but we don't write the 1. It's kind of understood that there is just, if I don't have that 1 there, we understand that there is just 1x squared right here. So it's the same concept, that if you don't see a base of 10, then you still have a base of 10. It's understood that that's common log. And down here you can see in the chart, these are the 4 properties that we just went through in the last examples. And these over here are showing you that those same general properties also work with a common log. And I'll just take the first 2 and prove those to you. It says that our first one, if you take the log of 1, it's equal to 0, no matter what your base is. So here, if you're taking the log of 1, again, there is a base of 10 there, so it's saying no matter what your b is, whatever your base is, your answer is still going to be 0. The second one's a little bit harder just to see visually, but understanding that log base b of b, if your base and what you're taking the log of is the same, your answer is 1. So here we understand that if we're taking the log of 10, if there's no base there, that's actually a 10. And you can see it a little bit better, that this is log base 10 of 10, and of course that's equal to just 1. And then you can see the relationship between the other ones as well. So just as a quick example, example 8, if you were asked to evaluate this without a calculator, there's no base here. So if you want to write it in, you can. And log base b of b, so my answer is just 7, and that's actually property number 3 up there. Okay, so we need to be able to recognize that log base b of b is just going to be, basically it cancels itself out. It cancels out to 1, and you're just left with the 7. Okay, and then the other type of logs that we have, so we have common log and then we have natural log. And the natural log, if you remember from, again, a previous section in chapter 3, we had something called the natural base. And the natural base is our e that we've been working with. And the natural base, we said, is equivalent to approximately, we just round it, and it's about 2.72. So the log function that has the natural base is called the natural log. So if we have log and its base is the natural base, so if it's log base e, we have a special name for that, and it's called the natural log. So log base e is called the natural log, and we actually have a special symbol or notation for that, and that's the LN button that you've seen on your calculator. LN is natural log. So we need to recognize or be able to understand that if we see log base e of x, we can rewrite that as ln of x, and they mean the exact same thing. So sometimes you may see log base e of x, sometimes you may see ln of x, but it's important to know that these are equal. They are the exact same thing. Okay, and it's just like with anything, there's sometimes you will need to write it as log base e of x, and sometimes you'll need to write it as ln of x. And we'll kind of see some of those examples in a later part of this chapter. So you do need to be able to make that connection and make that relationship. And just like with the common log above, you have your general properties, and then they compare that to the natural log properties. And they're showing that these are the same properties. Log base b of 1. If you're taking the log of 1, no matter what your base is, your answer is going to be 0. So here, understanding that when we see ln, we can also write that as log e, base e. So you can see it a little bit better if you write it out, that log base b of 1 is going to be 0. Now this one we'll actually deal with quite often, the second one. The ln, if I write it in its log form, log base e of e, you can see it's the same property as right here, log base b of b. This is log base b of b, so we know that's going to be equal to 1. So looking at example 9, ln of e to the 6th power, well, since ln of e is just 1, your answer is just 6 here. Now, one other thing that I've added in here that you kind of need to pay attention to is looking at the connection between the ln and the e and the process that they have that they actually undo each other. For instance, right here, hopefully you can see this connection that ln of e squared, the ln and e cancel each other out, and your answer is just 2. Here, the ln and the e basically just cancel out, and you're just left with the 7x squared. Here, if you have e raised to the ln of 2 power, the e and the ln cancel each other out, and then the same thing here, and all you're left with is the 7x squared. So one thing that we do need to keep in mind is, since natural log, or ln, of e is actually equal to 1, we're not going to actually write, you don't ever leave your answers just ln e, or natural log of e. Because it's equal to 1, we have to simplify down back into 1. So anytime you see a natural log and an e together, you can just cancel those out.